Okay, atomic radius. All right, back here in 8th grade Center on Demand. Like I said, back here in 8th grade Center on Demand. This is the atomic radius video. Now again, this is one topic, one of three in a series of videos I'm going to produce that allows us to delve a little bit deeper into the periodic table. Again, deepening our understanding of chemistry, getting us ready for the spring. All right, so let's take a look and work through this together. You've already done the POGL for Coulombic attraction. You've already done the other POGL, which talked about atomic radius and also ionization energy. So you have some background with this. So given this, I'm going to review a couple of example problems which compare the size of the different atoms. All right, so let's take a look at what the worksheet has first here. So you guys know a couple things you need to keep in mind: the concept of shielding and repulsion of electrons, number of protons in the nucleus, force of attraction between the positively charged nucleus and the negatively charged electrons, the way the periodic table is arranged, vertical columns of the groups, periods go across, and obviously valence electrons we know are the electrons found the farthest away from the nucleus, and they're the electrons that are involved in chemical reactions. So we've already talked about when we drew our board diagrams. Again, this is my first time with the smartboard video. Okay, hopefully you can see this pretty well. As you go down the group, okay, thinking back to the board diagrams, the size of the atoms get larger because you're adding energy levels of electrons. 1 level, 2 level, 3 level, 4 level, 5 level, 6 level, 7 levels. So as you add a level, the atom gets significantly larger, even though they're really small. But on an atomic level, they get much larger. And we showed as we go across, right, as we go from left to right across a period, okay, we said that we had the goofy song, row, because kids always forget rows, horizontal, period. Row, row, row your boat gently across the period. You row a boat horizontally over across a lake. So pretend you're row a boat gently across the period. You're out the table. Again, another corny sign. So again, if you look here, let's analyze this period right here, period 2. We know lithium has 2 electrons in its first energy level and 1 in the next. And it's got 3 protons. What's the difference between lithium and beryllium? Lithium's got 3 protons. Beryllium's got 4 protons. So beryllium has a stronger positively charged nucleus. So it's going to have a stronger nucleus, more protons. Then we add another electron. It has 4 total electrons, 2 in the first, 2 valence electrons in the second. So all we did was add an electron on the same energy level while increasing the strength of the nucleus, the positively charged nucleus. Therefore, because we're adding protons to the positively charged nucleus, we're increasing the positivity, the strength of the nucleus, but we're also adding electrons, but on the same energy level. So therefore, overall, as you go across, the radius will get slightly smaller due to the fact that, yes, we're adding protons and electrons, but on the same level. So the trade-off is it gets slightly smaller as you go across a period, okay? Well, let's look at lithium and sodium. Again, they're in the same family, and you're going to hear the song if you haven't already. We are family. Hey, hey, hey. I got all my valence with me. Whoa, whoa, whoa. What that means is they have the same number of valence electrons. Okay? They react the same way. You'll learn they both want to lose a valence electron. They're called alkali metals, some of the most reactive metals in the periodic table. But lithium and sodium. Lithium has 3 protons. Sodium has 11 protons. Right? So you think sodium has a stronger nucleus. Yes, it does. It has 11 protons. But look at the difference. If you can draw the board diagram in your head, lithium has 2 electrons in the first level, 1 in the second. Whereas sodium, hey, 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 goodbye sodium. Where sodium has 11 and 11 protons, so stronger nucleus. But here's the issue. 2 in the first, 8 in the second, but then we have to fit that last electron, 1 more, 1 in the third. So we have a whole extra energy level, a whole other level of electrons right there. That causes it to be larger than that. Even though it's got more protons, when you add a level, game over, larger size. So even with francium, I've got 87 protons. That's a lot of strength in a nucleus. But guess what? They also have 87 electrons. So it's got to deal with all those electrons, but here's the difference, 7 levels. okay? 7 levels of electron, the largest atom on the periodic table, right? Therefore, we've learned before that as you go down, the radius gets bigger, the force of attraction decreases. That's why francium, we've talked about it before, is the most reactive metal on the periodic table. It's the easiest one to lose, okay? So as we go across, the radius gets smaller because, again, more protons, more electrons, but on the same level. As you go down, you have more protons. But wait a minute, adding levels. Game over. Gets larger as you go down. Now, there will be a couple exceptions here and there. Okay, you'll get that in honors chemistry. I'm sure our buddy Mrs. Borstad up there, she'll get into why those exceptions occur. Again, we are kind of in the middle here between 8th grade and 10th and 11th grade. So she'll get to those couple exceptions, okay? But again, generally the trend is this. As you go down a group, the radius increases. As you go across a period, the radius decreases. So I provided this chart. Radius gets larger as you go down. Radius gets larger as you go this way. And you can also say this. Radius decreases as you go across a period. Okay, so you can write that up there if you want to. All right, good. So let's take a look at our first problem. Let's think about, given that information, let's think about how we should attack this. Now I've set this up in a way you can understand it. Once again, all academic all the time. 8th grade center pole and atomic radius. Here we go. So I've given you a list of 6 elements. Okay, and you have to use the periodic table. Now I'm going to look over there. Okay, because you know I have one over there. You should have one in front of you, okay? So you see, what I would do is write them down. Just write them down. Chlorine, helium, silver, Agnes loves her beautiful silver, francium, beryllium, I know it's beryllium, but beryllium, and fluorine, because that's how you spell it, but it's fluorine. Now, give me 1 second. I want to see if the pen shows up on the video. Oh, look at that. Awesome. All right, here you go. Hey, all you former students, enjoy this. Enjoy this. Hopefully you're using it too and get the periodicity. All right, here we go. Now, hey, you former students, don't get cocky. We didn't cover the whole honors chemistry course, okay? There's a lot of stuff we don't cover here. I mean, we are still in 8th grade, but great job so far. Keep up the great work, okay? But if you feel like you've already covered something, you're comfortable with it, study other stuff. Don't just sit back and chill. Study other stuff in chemistry, okay? Or manage your time and spend time on other subjects. Don't sit back and think you have less study time just because you know stuff already, because you learned it in 8th grade. Study other stuff in chemistry as far that you haven't gotten to yet, or get into your other subjects too. Balance the time. Do you understand? Don't you be pulling this, I'm going to sit back and chill because I know this already. I don't think so. Okay? Manage the time. Work on other subjects or push for AP Chem down the road. Study more in depth on other details. Okay, don't get arrogant up there. All right, here we go. So first thing you do is you ask yourself, what period are these in? We've talked about, as you go down a group, we said we add energy levels. So let's analyze what period they're in to determine how many levels there are. That will really help us. So when I look at the periodic table, I see that chlorine is in period 3. We see helium is in 1. Silver, Agnes, right? 1, 2, 3, 4, 5. Period 5, right? Double checking, it's my eyesight. Francium is in period 7. Beryllium or beryllium is in 2. Fluorine is in 2. Okay, so right now, right off the bat, do we look at every proton yet? Or can we start to fill some in? I think we can start to fill some in. Let's not worry about the protons yet. Hold off on that. So what to me is obviously the largest atom of this set of elements right here? It's obviously going to be francium because it's in period 7. So since it's in period 7, we're going to put francium right there, cross them out. What's next? Oh, silver, period 5. Okay, so again, let's put silver here, period 5. Oh, silver. Oh, chlorine, period 3. 3 levels of electrons. Let me double check. Okay, good. Chlorine, right? Okay. Now we have a tie right here, so we're going to have to do a little more analysis right here. But right here, very small, period 1, so it goes here. So now we need to determine who goes where between these two right here. It's like a tie game. What's the tiebreaker? Number of protons, strength of the nucleus, pulling the valence electrons in within the same level. So then you look at the periodic table. Now I don't listen, you obviously know beryllium is to the left side, fluorine is to the right. So since fluorine is to the right, the trend is the ones to the right tend to be smaller. I don't care yet. Analyze the protons. Understand it. So again, fluorine we have now has 9 protons. So now you revert to this information right here. Fluorine's got 9 protons, beryllium has 4 protons right here. So now, by looking at this information, right, we see that francium has more protons, stronger, more positively charged nucleus, more electrons to pull in. This is going to be smaller. And yes, obviously we can memorize that, yeah, these to the right tend to be smaller. But what is it dependent upon? Primarily the number of protons. So again, to rank them, we would then, and you take your time now, be careful. We have helium as the smallest. What's next? 9 protons, fluorine, then beryllium. Okay, so it should be helium, fluorine, beryllium, chlorine, silver, francium. Okay? So again, look for periods first. If there's anything they have in common, go for protons. Analyze the number of protons within the same row. Okay? All right, let's do another one, and then you're going to do the next 2 on your own. Or whatever. How many we got left? Okay. Oh, here we go. This next one up here. All right. So now we got this. Write down the elements. Whoa, whoa, whoa. Sodium. Na 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 na. Hey, hey, hey. Goodbye, sodium. Hey, by the way, shout out again. Oh, dine at Texas Roadhouse. I'm hungry just thinking about that. Oxygen. Li, lithium. Phosphorus, P. Magnesium, not manganese, Mg. Sulfur, S. Okay, now, what period are they in? So when I look over my periodic table, I know I have it written, but I like to double check to make sure I'm good. We see that na 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 na. Hey, goodbye, sodium is in period 3. Oh, that's annoying. We see, I hope I don't have lunch for you today. I don't think I did. Oxygen is in period 2. Lithium is in period 2. Phosphorus, period 3. Hold on, let me double check because I just got distracted by thinking about lunch duty. I lost my focus. Sometimes that happens when you study. Let me double check. 3, 2, because this is live, I'm not editing it. 2, 3. Take your time and double check. Good. Magnesium, 3. Oh boy, this is an ugly one. Sulfur, 3. Golly gee willikers. Yo, look at that. Of course I put something like that. Obviously we know that these 2 are going to be smaller than these guys. So these 2 are going to fight to go right here. These 4 will fight for these 4 spots. Now what's the tiebreaker? Why don't we attack the oxygen and lithium first, okay? So let's take a look. You know, you can memorize that oxygen is to the right, it's a nonmetal. It's all the way over in group 16 with 6 valence electrons in period 2. You know that that's going to be smaller than lithium. Okay, but let's go through the thought process. Look at the number of protons. So if I have oxygen has 8 protons, right? Here, I can put a little plus sign thingy right there. And we also have for lithium, 3 protons, okay? So looking at this, looking at the tiebreaker, this has less protons than this. This has a stronger nucleus, more pull, more force of attraction, more Coulombic attraction. Remember those words we talked about? So therefore, the smallest one is going to be oxygen right here. Check this out. Bam! Cross that out. Again, now these guys are in period 3, next energy level. So right here, lithium, right? Less protons. Boom, cross that out. Okay, now, what do we have to analyze next? Gee, I can memorize, oh, as you go left to right, the atomic radius decreases. I don't care. Think. Think about how the atom is, built. Think about the structure. So again, sodium has 11 protons. Phosphorus has 15 protons. Magnesium, 12 protons. Sulfur, 16 protons. Okay, so now, what's the game changer? Let's see, what's going to be the largest one? Why don't we go for the largest one? The one with the least amount of protons within that period. So the one with the least amount of protons within that period is going to be sodium. That's going to be the largest one. Okay? So sodium goes out here. Na 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 na. Hey, goodbye sodium. So then, okay, what do we have here? Right? What's going to be the second largest? The one with the least number of protons. Least amount of strength of the nucleus. So we're going to go magnesium right there. Like that. Cross that out right there. Okay? So now we're between these two guys now. You gotta be careful. Same period. Which has a stronger nucleus? Which is going to have more Coulombic attraction with the electrons? Is it going to be phosphorus or sulfur? The one that's going to have a stronger Coulombic force of attraction with a smaller, more attraction with a smaller distance, right? Because of the nucleus, it's going to be sulfur. So again, sulfur goes right here, phosphorus goes right here. Cross out, cross out. So again, we said to you, okay, I'm going to look at that answer real quick. Okay, you got it? Now real quick, let me scroll back up here. We told you, back with the POGL, yes, you guys in high school, we do POGLs here. We do POGLs here. Not as many as you do, but we do parts of them. Yeah, we do. Sorry, you guys in high school. You know we always evolve as the years go on. By the way, hail to pit. Okay, here we go. Now, so you look over here. Let's talk about these words. We have Coulombic attraction. I'm going to go F sub A, force of attraction. Right? And we're going to talk about, we're going to analyze that with distance. I hope you can see this. So remember back in the, oh, and I shouldn't say this given this football season, remember, go PV. What kind of relationship was that? It was an inverse relationship, wasn't it? Remember that with Boyle's law, right? Okay, so look here. As the distance from the center on out increases, what happens to the force of attraction between the positively charged nucleus and the electrons? It decreases. So right here, the force of attraction compared to the distance of the atom is an inverse relationship. All right? So as we go down here, the size of the atom gets larger, the Coulombic attraction is less. So if we think back again to group 1, how we have one valence electron right here, all these guys right here are all similar in terms of reactivity, group 1. But which one is the most reactive out of this bunch? Now they're all similar. But which one is the most reactive? It's going to be francium because they all want to lose one. But which is held the least? Which has the least force of attraction to that nucleus? It's going to be francium. That's why that's the most reactive. Does that make sense? Okay? And then we look over here, just getting ahead. We're at the halogens, the psychopath nonmetals, freaks. We look over here, and we all know that halogens, let me double check, hold on. Again, a one-man camera crew here. But again, we do it well here on 8th grade Son of Man. Where academics come first here. Oh shoot, I drew all that and you couldn't see it. Hold on. I really did draw that. See that? Hold on. What's this? Whoop. See that? Look. Whoop. Hold on. My bad. My bad. Look here. Where you at? Oh. See that? Force of attraction goes down as the distance goes up. We talked about that right there. Okay. Pause that if you need to look at it. Again, I'm new to this. Let me bring this on out a little bit. Okay. Oh, now we got room. Okay, now check it out. So now let's analyze over here. So we know these are, make sure it's on. Okay, so now these are the halogens. These are group 17. They want to gain one valence electron. We know they're called anions. So which one is going to draw in that valence electron the fastest? The one with the largest radius or the one with the smallest radius? So go back to this concept of distance and force of attraction, right? The smaller the distance, the greater the force of attraction. We want to attract one valence electron to get a full outer shell, because remember, all I want in science is a full outer shell, a full outer shell, yeah, a full outer shell. Gee, if I could only have a full outer shell, then I could be a stable substance. Remember that song? Okay. Remember acceleration, unbalanced speed up, slow down, change direction. Every time inertia. Remember that? I know you all remember that song. Okay, but anyway, back to this. So which one is going to be the most reactive halogen? They're all very similar in terms of reactivity, but it's going to be fluorine because it's got the smallest distance to the positively charged nucleus, therefore the greatest force of attraction. Therefore, that's the most reactive non-metal. Okay? So again, there you go. Nice summary on how to work those problems. Again, you want the last two answers? You can see me in class. I have the key right here. You can work it through yourself, and that's that. Hope you found this interesting. Hope you found that helpful, because hey, it's pretty cool that we're doing this right now. So next video, within the next week, we're going to have ionic radius, where we compare cations and anions, and we're also going to talk about ionization energy. All right, there you go. Atomic radius, Winter Wonderland Week, chemistry. Enjoy.